all over the textbook, but everything that we go over there's going to be in there, right? You understand? Okay. I know. I do. Okay. Wouldn't surprise me. It might be Unit 8 or something like that. So I don't know. I'd have to go back and look at it. So manual switches, manual contactors, manual starters, magnetic contactors, magnetic motor starters, contactors, and magnetic motor starters modification, the international standards and troubleshooting contactors and motor starters and motor drives, which we don't get into this semester, by the way. So a knife switch were first used to basically start and stop motors. So this is a knife switch. So very simple device. This is actually a single pole double throw. So we could actually control two different things with it. I'll pass this around and let you see it. Where's my camera at? Let me get my contactor out of the way. And these are still out there. Mostly they're used for disconnects. They're not used to control motors. So normally we have disconnects, and disconnects are designed to remove power from a system, right? You understand that? Where this would be able to move, apply power, but so it's got a knife. We call this a knife, and we call these blades for obvious reasons. So very simple to use. This is a single pole double throw. Oh, I'm sorry. It's a double pole double throw. So we got switches on both sides that we would switch to. So it's a double pole double throw. And this is kind of dangerous, right? So all this right here is electrically hot, right? You understand that? So you have to be careful around these things and make sure that you activate them with the handle. Disconnect. I'm not passing disconnect around because it is really big. So disconnect has some way to disconnect power, but it's also got some type of overload protection device on it. And of course, fuses are still very, very popular in the industry. And why is that? Yeah, they're a lot cheaper than circuit breakers. So this is a disconnect. So it's got 3 fuses, and we use these a lot in industry, where they're actually you have a case, and you literally have the ability to replace the element. So that makes it even cheaper. So it's inside ceramic, and you just replace the fused element when it blows. And so that would be a lot cheaper to replace the whole case. So this is a disconnect. So a disconnect is going to have a means to not only turn the power off to the system, okay, it's also going to have your overload protection devices. So we have disconnects inside our so that gray panel there, that's our disconnect. It's also got an e-stop button on it that we'll use, and it's got the ability to lock out, which is I'll keep the key to that. It's actually part of that. But that's a knife switch. You won't run into those very much anymore, except maybe in extremely old installations. This is what we got. We got basically a disconnect, but we don't have a knife switch as our disconnect. We have a disconnect relay. So we have actually an e-stop relay in there that disconnects. So relays are used a lot in e-stop circuits because it gives us the ability to push on a button and control a lot of devices. So basically, an e-stop circuit is just basically a sealing circuit. So we just come over here, and what's nice about this circuit is we can have multiple E-stops inside a system. And a lot of times it'll have a little thing like that, which means it indents, so it actually does what? When you hit it, it seals, it latches in, and then it's usually got a mushroom head on it. Now, how many of these can I put in there? A lot. Yeah. So we just have one, and then we come over here, and I'll have to figure out that circuit. That's not the right. It's not the same one. Seems like it's ours is a little different. So we have like maybe a reset. So on the ones that latch, some of them are different. Some of them you can just pull out, but a lot of your newer ones, once you push them in, you literally have to do what? Push them in and turn them and pull them out to make sure somebody don't. So on most of your new E-stops, you have to deliberately reset it, right? On ours, if you push it, if you pull it back out, it won't do anything until I come up here and do the key. As far as this guy right here is keyed, and then we'll seal in, and then we'll have a master E-stop right here. And then we could have multiple stations where we could reset it, or we could have multiple stations where we can. Okay, y'all understand that? Yeah. So, all your robots have to have a minimum of 2 E-stops, and one of them's on the controller and one of them's on T-Spendit. And then supposedly everybody that's working inside the work cell with the robot is supposed to have an E-stop button. So they use an E-stop control circuit, where you just take your E-stops and just hook them up, and then it electronically figures out how you got it. But it's so this is a manual contactor. So I've showed you one of those, right? We okay there? They've got where they seal the things up really, really well. We can still see the coil on this one. This one right here, you literally have to take it apart to replace the coil on it. But so this is the contactor. Here's A1, A2, so this is where we'd hook up the coil, and then so the T sides go towards your motor, and the L1, L2 goes to your that T side goes to the motor. So if you looked at the terminals on the motor, that's what they're labeled, and you jump them. It's going to be T1, T1, T2, T3. This is where your phases come in. And then you'll jump those depending on whether it's if it's a dual voltage motor, and you'll run into that a lot. You have to do some jumping on that too to set it up for. Ours is 440 or 220 or 208. So 208 pulls a little more current than 220, and a lot less current and then 440. If you wired it for 440, it pulls a lot less because it's rated in horsepower, right? You understand that it does work. But you have to rewire the motor to change the opposition of the motor. So if you raise the voltage and you want the work to be the same, then you got to raise the opposition, right? You want it exactly the same amount. So your current goes down. So double brake contacts break an electrical circuit in 2 places. We talked about that. What's the advantage of a double brake contact? Could be. The problem we have is we're dealing with electricity. And when you break circuits, we create arcs. The arcs are extremely hot, and they could cause the contacts to weld together. Well, if it's double brake, then what happens is it's spring-loaded. Each one of them spring-loaded. And if one of them breaks, it has a tendency to tilt. And we'll have a good chance of doing what? Causing the other side to break. So it's double brake. You make sure it breaks, which is right. But also it's a less tendency that if it does weld together, you'll have it'll free itself. So double brake, we run into a lot of double brake devices. And I think what I showed y'all was this control relay. And it's got double brake contacts on it. and you can literally tilt it either way. So if one side sticks, then when it breaks, it has a tendency to rock up. Yeah. So this is a control relay. This guy's here. I think y'all seen this one before, right? It's got like 8 contacts on it. Yeah, I did pass this around. Y'all want to see it again? So that's a control relay. A lot of contacts. Some of them normally open, some of them normally closed. And in those, you can really swap them. You can take them off and swap them depending on what you need. Manual motor starters, we have those. These have overloads on them. So our manual motor starter, if I can find one real quick. I guess I should have got these. So this is the manual motor starter. This is our manual motor starter. These are still very popular. If it doesn't have any control, those magnetic motor starters are fairly expensive. So we got a device. All we're going to do is control one motor. And these things, the contacts are basically on a V. So once you exceed a certain point, they open real fast and close real fast. So you can actually hear them when they actually change positions. We want the contacts to open real fast and close real fast to help extinguish arcs, right? You understand? And it's a motor starter because it's got overloads. So that's the overloads right there. So L1, L2, L3, this would go back to our 3-phase. And then T1, T2, T3, this would go down to the motor. So all 3-phase motors are going to have T1, T2, T3. It might have a T4, T5, T6, T7 if you have the ability to wire the motor for high voltage or low voltage. That makes sense. So our motor is a dual voltage motor. So that's why they bring the terminal down there so you can actually wire it. So we'll learn how to do that when we get to that. Y'all want to pass this around? Is this okay? Yeah, I didn't. That's pretty obvious. That thing works. Wiring diagram shows the connection of an installation of its components, devices, and its part. Right? We already talked about wiring diagrams. So this wiring diagram is really easy to read. We get some wiring diagrams that get very, very complex because they're trying to show you how all the devices are associated with each other. Where a line diagram shows you the logic operation of the circuit, it's a lot easier to figure out how it operates. A line diagram, all of these wires run all over the place, and you got to figure out where the seal-in is. You got to figure out that kind of stuff. So if in a wiring diagram for a dual element heater with pilot lights, the low heating element is operated when the low contacts in L1 and L2 are closed, so a connection is made to the low or common terminal of the heater. So what they're saying is this is the low heating element, this is the high heating element, and we just changed the two. And this is basically a wiring diagram, right? You understand that? I don't even know why we need this. In a wire diagram for a dual element heater with pilot lights, the high heat element is operated when the high contacts in L1 and L2 are closed so that a connection is made. That seems like the same one. Oh, okay. This one is low, and then this one is high. So I see the difference there. A manual motor starter is a contactor with an added overload protection device. So when we say motor starters, these are designed to run motors, but they have what? They have overloads. And we have two types. We have manual, and we have what we call magnetic. And the magnetic means it operates off an electromagnet, right? So, oops, going the wrong way, guys. The 3 stages a motor goes through during normal operation includes resting, starting, and operating under load. So what happens when we start that thing, it has a starting inrush current. It's going to be quite a bit more than what we call the full load current. And this is what they give you. So they give you this on the motor nameplate. You know what the nameplate is, right? Everybody okay? Yes, no? This is a plate they put on the motor that tells you all types of information. And if you take, later on, I'll show y'all the code where you can look up the basic start current on the thing. If you don't have that code, usually the rule of thumb is 6 to 8 times your full load current. Is what it would take to do what? Yeah, under load. That's what it should pull under load, okay, if it's going to run that. If you don't pull that, you know, and we on these big old horsepower motors, these big horsepower motors, we usually deliberately reduce the voltage on startup. We call it reduced voltage starters, so them suckers don't develop all that horsepower. I mean, some of these big 600 horsepower motors, you know, eight times that would be a lot of horsepower. That thing would tear stuff up if you turn that thing loose. So a lot of our motors, we deliberately reduce the voltage on the input to cause them not to be able to do what? Generate that horsepower, and then when they get up to speed, we switch them over to their primary voltage. Call them reduced voltage starters. So we deliberately keep those things from developing all that horsepower. So if your voltage is the same, then your power would vary with the current, right? And if the current's 8 times more, then it's going to develop what? It's going to develop 8 times more horsepower. Are we okay? A three-phase motor goes through, so we have resting, we have starting, and this is where we start it. And this is where it's got that inrush current, right, when we're trying to start the things. And then we have the load current. So that current rating on the nameplate is what? That's your full load current. That's the current the motor should run if you're doing what? Running at its rated horsepower at its what? At its rated voltage. If you're running it below its rated horsepower, it's not going to pull that current. Are we okay? So that's a pretty standard curve right here. A lot of current to start off with, and then when it starts dropping off instantly as soon as the thing starts rotating, right? You understand? Then it levels off, and then it should run the same. If we keep it under constant load and we don't change the load. If your load varies, then the current will vary. So this is the problem we have. So an overload does not open the circuit while the motor is starting. So your fuses has to let the motor start. So if I've got a certain horsepower motor that's supposed to pull 10 amps when it's running, and I fuse it for 10 amps, every time I start it, it's going to pop our overload protection device, right? So we got to set those fuses at least 125% of that surge current. So you don't rate fuses at where you want to blow them, you rate them above, right? And then you go to the next standard value. So rule of thumb is 125%, round up to the next standard value. That's the way we size fuses. So if we set that and the motor stalls or the motor don't start, then we'd burn it up. So that's what overloads do. We okay? So ours has heater overloads. So they drop very little voltage, guys, but we're pulling a lot of current through them, right? You understand? And they literally heat up. And I think I told you it has solder in there, right? And it's spring loaded. And when the solder melts, it does what? So these you're gonna have to let them cool down. You can't if you're there when they pop, and you sit there and press it, it's not going to do anything, right? You need to let them cool down and let that solder set back up in there. So this is a pretty good example right here. Eutectic alloy tube. Eutectic, we can't quite get eutectic solder. Eutectic, a solder is an alloy. And what is an alloy? It's something made of at least what? 2 metals. Yeah. Well, solder, most solder is made out of lead and tin. And eutectic means it has no, if you get the ratios right, they have no plastic state. So 63-37, if you had 63% lead and 37% tin, solder would melt at like, I forgot, 600 and something degrees. It would turn into a liquid, and if it dropped down below that, it would turn into a solid. And that's what eutectic means. It means it has no plastic state. Steel doesn't have that, so thank goodness. That's the way we shape steel. We put it in a plastic state, and then we roll it into the shapes we want, right? So eutectic solder has no plastic state, so it goes from a solid to a liquid when you hit a certain temperature, and as soon as it drops below that temperature, it turns back into a solid. So that's what eutectic means. It has no plastic state. Eutectic alloy combination to activate a trip mechanism when the overload occurs. So this is it right here, guys. I missed it. I said 600. It's 300. It's 600 and 361 degrees. Tin lead. So pure lead and then pure tin. So 6337 has no. It has no plastic state. So you can see right there. So at 361 degrees, it would turn into a liquid. If you drop below 361 degrees, now for some reason, which I've never quite figured out, this is the standard solder we usually use in electronics, 6040. So it has a what? It has a slight plastic state. So if you let your wires move while you're going through that, you'll get what we call a cold solder joint. In manual motor starter, overload relays, the compressed spring tries to push the normally closed contacts open under normal operating conditions. So, are we okay? Yes, no? Don't let me go too fast. Reset, everybody okay on the reset? So, but you need to let them, if it's using heaters, you need to let it do what? Yeah. And by the way, this is one thing I kind of like about heaters, is that if you change the voltage, it pulls less current, you have to change the heaters. So when you rewire it for high voltage, you go to a different heater, because the heater don't care about volts. The heater's looking for current. So if the current goes down, it's not going to trip at the right place, right? And you still could burn your motor up. So these heaters are replaceable. And they're in series, they're wired in series with the motor. So this is our motor starter that we'll use. We got two. This one's the easiest one to use. So here's our heaters. And you can see it's just got two screws that I could do what? Take it loose and break it out. One of the things we'll do is see what we do to figure out what size heater to put in there. So a lot of people don't know that. They'll rewire the motor. They'll have a two voltage motor. They have a dual voltage motor, and they rewire it, and they don't come up and do what? They don't put the right size heaters in there, and then that way they can still burn their motor up. So, but you have to replace the heater. You don't have an adjustment. You can just keep turning up because your overloads are tripping, which is the next one. I'll show you that one. Are we okay? Y'all see, it's very easy to replace this thing, but you got to figure out, you got to put the right ones in there. So each manufacturer will have a table that you would use depending on the current that your motor pulls. When you you set it on your full load current, and that it lets pass, right? It lets the full load current pass. Electronic overload has a built-in circuitry that senses the current. It's usually a little what we call current transformer. So this is the other magnetic motor starters that we have. I passed that one around the other night, right? You okay on that one? So I'll pass this one around. This is another one that y'all can use if you want to. So this is an electronic. So this is electronic overload. And this right here is where we set the value at. Now what's the problem with that? So your maintenance guy, the motor loads trip, what's the first thing the guy's going to do? And then what are they going to, if it trips again, what are they going to do? They're going to turn that whole thing up. Right? You understand? and it trips again, they'll turn that little thing. It don't trip now. And then your 2000 motor stalls and burns up because some idiot did what? They didn't do the math to set that overload to the wrong value. So this is a good idea. I mean, I like it. It's ease of use, but you need to go through the system and make sure you set this thing for what it's the motor you're running. Right? That makes sense. Oh, yeah. So these, you have to change the heaters out of them. So the electrician can't do what? They can't come in. They could put bigger overloads in there, but it's a little more to it than that. So these are electronic overloads, and basically, so we have a contactor, and then we have an overload. So they sell the contactor by itself, and then the overloads are just attached. In fact, over there on the manufacturing line, they've literally got an overload over to the side. It's not even mounted by the actual relays that it works with. So this is a magnetic motor starter. Now the big difference is that if you decide to use this one has the wiring diagram on it for you. This one don't. So if you decide you want to use this one, then what does that mean? You got to get the data out and find it and then figure out how to wire it up. So this is a magnetic motor starter. By the way, you can look on the side and it tells you the size motors that it will run. 1 horsepower, 3 horsepower, and this is what we call a size. I don't see it on here. It's probably a size 0. I found in my that's one of the main differences between women and men. Is men, if they got something to turn or they got something to switch, they're going to do it and to see what it does. Well, most women will say, well, ask what it does before they make anything. So, and that's a problem. If we got a dial, if we got a switch, Michael might have heard the story before. We got a manufacturing over the line. It's got a bunch of knobs and stuff where we turn all this stuff on it. And the guys from Brosa was out there, and they were taking pictures, photo ops. And they said, act like y'all doing something. And guess what they acted like they was doing? They started turning what? They started turning knobs. And nothing would work. We got back over there, and the line wouldn't work. Act like y'all doing something. So, true story. I can't remember. I think that was the first group. I think that was Kurt and them. So. Manual starters are selected considering the phasing, the number of poles. Y'all understand poles, all right? Poles and throws. Voltage, starter size, and the enclosure type. You can see the difference over time. When I passed that control relay around, the contacts were exposed, right? You understand? On most of your new control relays and your new motor starters, those contacts are sealed up. So they seal them things up where you can't really get to them. And one thing they do when they seal them up and they electrically isolate them from each other is they have a tendency to blow the arc out. It's just like when you're in a swimming pool and you put your hands together and you move them apart real fast, the air does what? Yeah, it shoots between there. Well, we try to do that with contacts, but we don't want an arc from another contact getting over to this contact, so they have them in troughs, and they seal them up. So that way, when they open real fast, it has a tendency to blow an arc out. So that's something. So these contacts open real fast, guys. AC motor contactors can be divided into single phase and 3-phase. We have a single wired. Usually 120 we fuse or put the overcurrent protection device in only one side. When we get up to 240 or 230, we usually break 2 sides of the line, right? You understand that? We'll have double fuses, and then 3-phase we need to put a overcurrent protection device in all 3 phases. Originally they thought that Okay. All we need to do is protect two phases, and the other one doesn't matter. But they found out real fast that it does. So we got a motor starter up here. This is a gigantic one. So I think this is a size. Oh crap! I think this is a size 3. This will run up to, but they only have 2 overloads on it. So here's the overloads, and they're actually separate. So this would not be legal in current. So it only has 2 overloads, one on this side and then one on that, and it's got 2 resets. So what we would be doing, we'd come over here and reset this one. So somebody, you'd need to know to do what? Reset them at the same time. So if you reset this one, you're going to single phase the motor if it's got power to it. So on a 3-phase motor, if you connect 2 phases, it sees it as single phase, and the motor will just buzz at you because it doesn't get that rotating feel that we get out of a 3-phase. But it's only got 2. So today this would not be legal. I'm not going to pass this guy around. It's but this guy here, 440, 5, it'll run a 10 horsepower motor, single phase, or a 25 horsepower 3-phase. This thing is heavy. I bet it weighs 15 pounds. But you won't run into that. You won't run into that anymore. So they thought if they broke any 2 phases, but still that one still had voltage on it relative to common, so it still could get people hurt. So now they fuse all 3 phases. Manual motor starters are used in applications such as conveyor systems and drill presses. Control relays is the relays whose contacts are used within the control circuit and not intended to run high power loads. We already talked about that, right? Are we okay? Yeah. So control relays. These guys, they can be sealed up. A lot of them you're going to see is these little, we used to call them peanut relays, and how they got that name, I don't know. But the contacts themselves are actually sealed in a plastic enclosure. And they usually have more than one throw, more than one pole. So our control relay looks just like that. If I can find one. Oh, here it is. I think I've already passed this around, right? Yeah. By the way, most of them have what we call a manual override. You have to be real careful on that. So some of your control relays don't. Most of your motor starters have a manual override where you can literally push the contacts together with your hand. You need to be really careful and cognitive of that when you do that, right? So we had a guy out at U.S. Steel working up in number 8 blast furnace. Number 8 blast furnace was it was a positive pressure furnace, and it was a continuous casting furnace. So what they did to keep the pressure in the furnace at the right pressure, they had a conveyor belt that would carry material up into the top of the furnace. They would open one hopper door, and they would close it, and then they would open the bottom hopper door. They'd open the bottom hopper door and let the material fall into the blast furnace. They had a guy up there having problems with one of the hopper doors, and they went in, they locked it out, they did everything, and he sent a guy down there to activate that hopper door, but they didn't lock out the other one. So he pushed in the wrong one and activated that hopper door, and it came up and killed the guy. So, like I said, when you override the control circuit, all the safety that's built into it by manually operating these things, you have to be pretty careful. I almost caused a big problem on number 4 galvanizing line. That the strip that they put the tin on to galvanize it, that thing ran like at 700 feet a minute. And when it welded strips together, it had a strip welder that'd stop it, that'd bring down side clamps, clamp it down the strip wouldn't move, and then that weld trim it and overlap them and weld two strips together. Well, I was in there pushing in a relay, and I was pushing in those side clamps, and the thing was out there running 700 feet a minute. Luckily that day they was running a narrow strip, and the clamp was missing the thing. If that thing clamp would have came down and caught that thing running at 700 feet a minute, that'd probably still be cleaning up 10 out there, because it would have just buckled and done everything. So you've got to be really, really, really careful when you override relays or override. You need to be cognitive of what you're doing, what's going to happen, because all it takes is just, and I think I showed you that one on this one, right? The manual override. So there it is right there. So I got all this fancy sensors. I got all this stuff out there controlling this. This thing's running a motor. I come over and push that thing in, that motor takes off. All those sensors that sense if a person's there, if everything's in the right place where it's supposed to be, is no longer comes into play. But it's a very, very valuable troubleshooting tool, right? But you got to do what? You got to know what you're doing, and you need to know the consequences of your actions. Contactors are used to make and break the electrical power circuit to lights, heaters, transformers, capacitors. The contactors may also have one or more auxiliary contacts, and the auxiliary contacts are going to be in the control circuit, right? You understand? Yes or no? So I could have a motor starter that's got a sealing circuit. I mean, where's one of my blank ones at? Here we go. So I could come over here. Of course, here's my power circuit. So I'm gonna come over here, and we'll call the motor starter. We'll call it M, but it might have a different name, right? It's just that's very convenient. So here's the contacts, and then we'll come down and we'll have an overload sensor. So these are the sensors that sense the overload. And then it's a three-phase motor, so this would be my stator. And then up here, this is probably where our fuses are going to be at. And of course, this will be L1, L2, and L3. By the way, some companies call them phase A, B, and C, so don't be surprised on that. And this is the actual motor. So this would be my power circuit, right? This might be 660 over here. And then over here I have my control circuit. And all I want to do is stop the motor. So I'll have a button that we'll call stop. And then I'll come over here, have a button, normally open, we call start. And then I'll come over here, and then I have my motor starter. And then we have overloads, right? That's your overload. So we know we don't wire that. That's going to be wired internal to the motor starter. And then I want to seal this in. So if I'm going to seal it in, I can come over here, and we'll come over here and put an M. Well, this is going to be an auxiliary contact. So it's going to be small, right? You understand? It's not going to be near the size of these guys over here. These guys are designed to handle a lot of current because they're over in the power section. So most control circuits, but this relay is not only controlling that contact, it's also controlling these contacts over there in the power circuit. It makes sense? So, yeah, the relay would probably even be over in the power circuit. And then I'd run wires all the way from my control circuit over to the power circuit. Right? That makes sense. So that auxiliary contact, that'd be an auxiliary contact. It's going to be small. It's probably going to be strapped on the side of the motor starter, the magnetic motor starter. And that's what we usually use for stuff that's going to go on inside the control circuit. Okay, double break. Let's see, here. I know y'all about ready to take a break. Overloads. By the way, that's not going to be in your. This is one I got out of a manual when I learned how to solder in the Navy. So, let's see. Yeah, control relays, power circuits. We talked about solenoids, two-wire control. So this is the problem with a wire diagram. So I've got a control circuit in there somewhere, but I've got to figure out where it's at, right? We know what we'll find out is they put the coil on one of your power leads. It's usually going to be on the L2. So that's the coil right there. And then I got to figure out, here's the fuse. We'll come down, and then this is a real simple circuit. I got to come in, and I've got to figure out, that's a C, that's that contact there. And I don't see that on the motor control circuit. We got this guy right here. And so that's the control circuit. And then this right here is the actual power circuit. Doing a different color. This looks like it's a three-phase heater to me. So this is not a motor. And then we get down here, this is the control diagram, and to me, it's just so much easier to try to figure it out than trying to pick the control out of the wiring diagram, right? You understand that? Oh, here we go. So there's this is the same thing. We know that if it's got these dashed lines around it, what does that mean? They're in the same unit, right? Inside the same case. And so I'm trying to pick out this start stop in this sealing circuit when down here it's drawn in using ladder logic. But it doesn't show me how everything is oriented between. It don't show me that this button and this button right here is inside the same unit, right? You understand that? So it's one to the other. It's whichever one you see. But to me, these guys up here are just impossible to figure out, especially the logic of the circuit. So this is so up here. This is power. So this is our power. And this down here is our control. Are we okay? Makes sense. We okay? A step-down control transformers use to step down the voltage to levels required in the control circuit. And like I said, originally we had most of your stuff was built around 120 volts because that's what houses had. And that's before the National Fire Protection Association came out with what they call the 70E standard. So 70E, which is what protects you, they decided that anything over greater than 50 volts they consider this to be lethal. What does that mean? It means if you work in over, that's 50, Rich, not 5. So as soon as you get above 50 volts, your PPE requirements go what? Up. So most of your control circuits now are like 26 volts. If it's AC, it's 26 volts. If it's DC, it's 24 volts, which is pretty standard especially in programmable controllers. So that's well below the lethal section. So now you can work inside the control circuit, and you'll have on a pair of safety glasses. If your company requires a hard hat, you might have that on. Long sleeve shirts, right? And then non-flammable cotton, by the way, is required, and long pants. And then the shoes you have on, these are leather shoes, or a lot of companies require steel-toed shoes, and some companies require metatarsal protection, which is the top of your foot. So out of U.S. Steel, that was our standard PPE with safety glasses, hard hat. Of course, we always wear long pants. They didn't make us wear long sleeve shirts, and steel-toed shoes with metal tarsals. Contactors have either AC coils or DC coils. Everybody understand that? So the coil, what we're controlling and what we control the coil with don't even have to be the same. So our control circuit could be 24 volt DC, and then the coils have 24 volt DC coils, but they can be controlled hundreds of volts, right? You understand? They can be controlled because it's just a switch. It's just like that switch back there allows you to control 120 volts of push, right? Has nothing to do with what we're doing. So all the coil does is cause the contacts to change states, but they're just contacts. All you're worried about is that if you see, so contacts are usually rated at a voltage and they're rated at a current. A voltage rating is how much voltage, how much push they guarantee they can break. Because that push is there. It's trying to push current, right? It's trying to push that current. And if you don't, if the contacts don't open fast enough or they don't open wide enough, what could it do? It could arc across and keep arcing. So it's how much voltage they can break, and then how much current you can get through the contacts. So if you go back and look at relays, the breakers on for your house, it's going to be rated at a voltage, and it's going to be rated at a what? At a current. Electrical arc is created between contacts as they are open. Prolonged arcing may result in damage to the contact surface, and they could literally do what? They could literally see it. They could. Now, normally we don't file these things. That's not true. We have what they call a burnishing tool. It's a really, really fine grit to it. You don't want to file these contacts with a file because usually they are silver coated. They're silver plated. And if you get that silver off, what's going to happen is it's going to work for a while, and then after a while it's going to oxidize and you're going to get problems. So just that burnishing tool, that's about the only thing you should clean these contacts with. You hold them closed and then make sure there's no power on and pull them. Are we okay? The maximum arc current is reached only once during a half cycle of AC, so we know that. Okay, so arc chutes. We understand that now. So the contacts are inside what we call arc chutes, right? So they're isolated from each other. And why do we want them isolated from each other? Well, if you get them too close together, you got two polarities side by side, right? You understand? So we put them inside chutes, and then we also do what? We seal them up now. And when we seal them up, it has a tendency to cause it to self-extinguish. Okay, let's take a break.